Alrighty. All right. So this is the force of a magnetic field on a moving particle, right? It has this charge, so that's the charge. That's the velocity, right? That's the magnetic field. And then if there's an angle between the velocity and the magnetic field that's not 90 degrees, then we have to use the angle between the V and the B. Okay. So if I've got a magnetic field, let's say I've got a particle here. Start with a positive particle, right? Because keep in mind that if this is a negative charge, right, it puts a minus sign in there, and so it's going to be negative the direction you figure out, right? So if I've got a particle that's going, say, exactly to the right, that's its velocity, and the magnetic field is maybe like this, right? Then we're going to use the sign of that angle between them, right? To the point where if the particle is going parallel to the magnetic field, this is the magnetic field here. Okay, if it's going parallel to it, there'd be no force at all, and there's a maximum force if it's 90 degrees. Okay, remember that this is in the right hand direction. Okay, so if I've got, say, a magnetic field coming out of the page here. There we go. So many dots. So I got to draw more. It's got to be square, right? Okay. And let's imagine that I've got this particle that is a positive particle, and maybe it's going to the left here. Okay. If we do the right-hand rule, okay, this is our velocity. Right? If we do the right-hand rule, our index finger is this guy, right? Our middle finger is this guy, right? And our thumb is this. So if I put my finger to the left, I put my middle finger out of the page. That's what those dots are for the magnetic field, right? Okay. Then the force on this particle is this way. Okay, which makes it go in a circle. Ooh, look at that nice circle. Okay, it's not a nice circle, but it's close enough, right? So because when the particle is going up, the force will be to the right. It's always at right angles to the velocity. So it doesn't speed this particle up; it just changes the direction. They use these in particle accelerators. That's why cyclotrons make particles go in curves, paths, right? That's why the superconducting super collider makes particles go in a big circle. Okay. They use magnetic fields to do that. And then the key thing here is that we can say, if this is all right angles there, the sine of 90 would be 1, and we can say that the force is just QVB. And then if it's making it go in a circle, that magnetic force becomes a centripetal force, right? So now we can calculate the radius and everything like that. And that's just a key thing. So it's like, there's a whole series of problems where the centripetal force equals friction, centripetal force equals the tension in a string. Here, the centripetal force equals the magnetic force. So that's a whole genre of questions. Okay. So that's this guy, right? So Q is charge, plus or minus, right? V is velocity, V is the magnetic field. And then F is, of course, the force. This one should be, and by the way, this should be written in college. You'll see QVB cross or QV cross B, right? Which makes it QVB sine theta, right? So it's actually a vector cross product. This one should not be allowed. Nobody should ever write it that way. It should be I L cross B, right? Which you could write ILB sine theta, but nobody. I don't know. I mean, I understand that they're just writing this as the scalar part of it, but yeah. Anyway, sorry. It should be written this way, in my opinion. Okay. And so this guy is for if you've got that same magnetic field, right, and we've got a wire. I'm just going to draw that much magnetic field. You're going to have to live with it, right? And let's imagine we've got a current going this way, okay? And then this is our magnetic field out of the page here, okay? For the same way that we got a force on a positive particle here, we're going to get a force on this wire. So our index finger, again, index finger goes in this direction, right? Our middle finger goes in that direction. If this makes no sense to you, and if you learned a different way with your hand and your wrist, ignore what I'm saying here. And then this is the thumb. the thumb goes that way, right? Because when I learned it, it was like you put your right hand in the direction of it, and you, anyway, bent it or something. I don't know. All right. So anyway, with this guy, if my index finger is pointing that way, my middle finger's out of the page, there's going to be a force on this wire that way. Okay. And then L is the length that the magnetic field and the wire overlap. Okay. So that's what L is. I is the current in amperes. Right? It's not the amperage, it's the current. Okay. L is the length in meters, and that's the magnetic field in Teslas. And then if there's some angle between the wire and the magnetic field, just like in the case of the, so like, let's imagine we had a magnetic field that's like this, right? But our current is like this. We'd use that angle. That's our theta. If this is B and this is our current, we'd use the angle. We put them tail to tail, find the angle between them. Don't be afraid to use, big angles. Obtuse. Obtuse. All right. And then that last formula there, this is the force between two wires, the force per unit length between two wires. Mu naught, that's fun. That's 4 pi times 10 to the minus 7th Tesla meters per amp, right? So, and that the funny thing is that the constant ended up being close to it, right? So then they just rejiggered all the units, like coulombs and stuff, so that it was exactly equal to 4 pi times 10 to the minus 7th, which, seems counterintuitive. Okay. Nature's not that beautiful, but it is if you try. Right. So the idea here is if we've got a wire here, we've got, say, I1, and then we've got a wire here, and this is I2, and they are R distance apart. Okay. And then they overlap for a length of L. Right. There's going to be a force on these wires. Okay. This, by the way, and that's, that's really all you need to know. Okay. This is the force. And in this case, I think these guys attract each other. And I'm just going to go on a tangent here, but I'll show you why they attract each other. I'll show you where this thing comes from. Let's just have some fun here. Let's use some red ink just to be kind of crazy. So let's take this wire here and let's say that it's going to create a magnetic field. As you know, okay, it's going to create a magnetic field into the page on this side, right? And out of the page on this side. As if we were to look at this thing from this point of view, okay, looking down, it circles anti-clockwise around that wire. That's the right-hand rule for wires, okay? In this case, we've got a current going up the page. So if I put my index finger up the page, middle finger down into the page, the force on this wire is going to be to the left. Okay. Now, wouldn't it be interesting if the force on this wire was also to the left, and we could create like this Newton's law defying, propulsion system, right? So let's look at it as if this guy creates the magnetic field, this guy responds to it. Let's choose a different ink color. Let's try green. Okay, so due to this wire, the magnetic field is into the page on the right side. And due to this wire, okay, the magnetic field is out of the page on this side. Again, circling this wire, if you looked at the end of the wire, the current's coming at you. The magnetic field makes circles around conductors that are anti-clockwise. Okay. Now, if I do the right-hand rule on this wire, of course, my index finger now goes up the page, middle finger points out of the page, and now the force on this wire is, where's my cursor? There. The force is to the right. Okay. And these are the equal and opposite forces, right? These rules couldn't work unless these forces were equal and opposite. So anyway, that's that, right? And then, you're asking, the astute student asks, well, where did this formula come from? Well, this formula lets you do a whole bunch of really cool stuff, right? Okay. And this is the idea, right? Is that if we have a wire like this, Ampere's law says if we do an integral of I don't know, I'll call it L or something like that, distance, right? If we integrate the the magnetic field over a distance in a circular loop around the wire, it'll equal mu naught times the current contained. And this is one of Maxwell's laws. It's also Ampere's law. I'm not sure I'm writing it correctly. dx, maybe they do dx. I don't even know. Right? So some unit of distance. We're going to integrate it, right? And then imagine that we integrate in a perfect circle a distance r from the wire. Okay, we're going to just integrate in that circle, right? Well, if we integrate all the distance in that circle, the integral of a complete circle of radius r is just the circumference, right? So we get b times 2 pi r, right, is equal to mu naught I, right? And then you can get that the magnetic field around the wire, some distance from it, is just mu naught I over 2 pi r. Which is kind of fun, right? Because mu naught is 4 pi times 10 to the minus 7th divided by 2 pi is just 2 times 10 to the minus 7th, right? Okay. But anyway, that's that, which just means that surrounding wires, there's magnetic fields. They're not very strong. So when I demonstrate this, I use, many, many windings of wire, each with 5 amps in it so that I can get like 50 amps. And then the compass can respond to it and stuff like that, right? So it's not a strong magnetic field, but there it is, and it circles the wire. And then, of course, if I stick another wire a distance from this, and it's parallel, even though I can't draw parallel lines, right? And this is I1, and this is I2, right? Then I can say that the force on this wire is just I1L, where L is this length, times the magnetic field, right? Well, the magnetic field is this, right? So it's I1L, and then the magnetic field is, this is I1, this is I2, right? So it's mu naught I2 over 2 pi r. And then all I have to do is just divide both sides by L, and I've got force over L, if we can write it this way, right? And then we've got mu naught I1, I2 over 2 pi r. Isn't that a pretty thing? Okay. Now, back in the day, they used to define the ampere in terms of the force per unit length on two conducting wires, right? They don't do that anymore, which I learned last year after, I think, teaching it wrong for several years. The main thing in teaching is do no harm, but I definitely did some harm there. But then last year, like, oh, I think a student that you guys know would inform me that I was teaching it wrong. I was like, oh, by God, by gum I am. All right, that's all I can say about that.